Hello everyone, and welcome back to another remote sensing lecture video. And in this video, I want to sort of circle back on our idea of spectral response curves, which again, to sort of quickly recap, right, we said that we can take, in this case, reflectance or radiance. Again, it depends on what you're measuring here. Just be careful that you read this. And we can draw that out as a function of wavelength. And what we'll get is we'll get a curve that sort of describes the way that an object interacts with radiation at whatever wavelength regions we're measuring. So in this case, we went from blue all the way through NIR. And I want to circle back on that for a second. And I want to talk about what is actually causing these differences. I'm not going to get into like specific details about specific objects, but I want to just in general sort of talk about to go back up to our original point here, right? Where we said that this reflection is wavelength dependent. Well, I want to talk about just broadly, what makes this wavelength dependent, right? What things do we consider, or what things are being considered about an object that make it wavelength dependent? And hopefully I'll also tell a brief story here about why we care about this, or maybe a better way of saying that is a real life example of this wavelength dependency in play. So let's go ahead really quick. And what I want to do is I want to actually start with a story. So let's say that you are sitting in your house. Right? So we're going to draw a nice little wall for you. Right? So you're sitting in your house. Right? Here's the wall of your house. Right? Wall. Okay. And let's just say that for starters, you're sitting in a dark room. So here's you. You're sitting on a chair, right? And you're listening to the radio, right? We're going to say this is old-fashioned, right? And we have a radio. Okay. And for whatever reason, you really like to sit in the dark. So there's no lights on in this room, right? You're sitting in the dark, listening to the radio. Let's think for a second. Oh, actually, I should say one more thing. We're going to assume that it's bright outside, right? It's nice. It's daylight. It's noon on a Sunday, and you're inside a dark room listening to the radio. Well, let's talk about that from an electromagnetic radiation perspective. Let's talk about what's actually happening here. Well, the radio is you're listening to the radio. So what does that mean from a radiation perspective? That means that somewhere, kind of nearby, right, there is a radio station. Right, and this radio station is emitting a wavelength of radio wave, which is again electromagnetic radiation, right? It's emitting a wavelength. And that wavelength is able to pass right through your wall to your radio so that your radio can pick it up, interpret it, and spit it out as music. And that's what the radio station is doing. This radio wave, so this is a radio wave, right, is able to pass right through your wall, hit the radio, and you can use it. I also said, though, that it's noon, right? It's a bright, sunny day on a Sunday. And you're sitting in a dark room. Well, what does it mean, the fact that your room is dark? Well, what that means is that this light that came out of the sun, right? The sun is emitting all kinds of waves. Right, actually, let's make it curved so it's a little more realistic, right? Really high frequency. Right? It hits the wall, it doesn't make it through to the room, right? Because if it did, your room wouldn't be dark. So it's being, either reflected off the wall, or it's being absorbed by the wall, or something is happening in this wall, so that energy coming from the sun is not lighting up the room through this wall. But yet the radio wave being emitted by an antenna at the radio station can pass right through your wall just fine, and your radio is able to pick it up and everything works. So you can see by this example, this is sunlight. This is sunlight. Right? In this case, the wall is preferentially allowing radio waves to pass through, right, transmission, but the sunlight is not. It's being reflected. So this shows you that the wall, right, has different properties, different interactions with the radio waves than it does with visible light. Okay, so let's look at another example that'll hopefully make this even more concrete. So we're going to have, again, right, we have a wall, top and wall bottom, but in the middle of that wall is a window, right? So this is a window. Okay, now, so you've decided you're done listening to the radio, you really want to get some light. So you go ahead and you move your chair. So now this is you. You're now, that's a really bad drawing of you, but you're now sitting in front of a window, right? And again, we have the sun, okay? So if you look at the window specifically, what you'll see here is you'll see that it passes through the window, right? You look outside, you're able to see the outside, right? Light is passing through the window. It's being transmitted through the window. But if you look around the window, at the window frame or at the floor or the wall, right, you'll see that you don't see the sun, right? You don't see the sunlight. It's being reflected off. So in this case, right, you have two different objects. You have the wall and you have the window. And you can see that even though both of them are dealing with the same sunlight, right, this is sunlight in both cases, right, the window is treating it differently. It's letting it pass through, versus the wall is either absorbing it or reflecting it. Okay, so in this case, we have the same object dealing with two different wavelengths differently. In this case, we have two different objects dealing with the same wavelengths differently. So hopefully this sort of solidifies that idea that these interactions are wavelength dependent. So now I want to sort of ask the question, well, what drives these differences? Well, not, but help if I could actually spell and had decent handwriting. What drives these differences? Right? What makes the wall interact differently with the sunlight than it does with the radio wave? And there's really two things. The first is the chemical composition. All right, what is that object made out of? What sort of chemicals are in it? Does it have water? If we think about a leaf, for example, right? What's in a leaf? We have water, we have tissues, we have chlorophyll, which we'll talk a lot more about chlorophyll later, right? But there are certain chemicals, right? And there's certain things that are inside of the object that are going to absorb, reflect, or transmit energy, right? So this chemical composition, right? This is generally or typically or tends, I'm going to use the word tends. Nope, there's no R in two. This tends to drive differences at shorter wavelengths. Right, short wavelengths, right, visible, ultraviolet. If we were to go all the way to X-ray, right, lead interacts very differently with X-ray than human bones do. Right, chemical composition tends to drive the differences at shorter wavelengths. The second is physical factors. So this is going to be things like size, shape, maybe orientation. All right, is it tilted? Is it not tilted? Right, this is going to tend to drive differences at longer wavelengths. Right, so we're going to go through an example in the next video of some sort of examples of where we see these differences. So hopefully this made sense. Hopefully my amazing artistic skills up here really drove that point home that we have differences based on wavelength. And then hopefully this makes sense about the things that we need to consider driving these relationships. So hopefully this made sense. If any of this was confusing, I encourage you to pause the video, go back, rewatch the parts you're confused about, and as always, please reach out. Thank you.